Hi, welcome in the fourth part of the ultraviolet and visible spectroscopy. In this video, we will discuss the Woodward-Fieser rule for the diene and trine, types of diene and the nature of double bond present in the diene, and the calculation of lambda max for various dienes. So let's begin with the Woodward-Fieser rule. In 1945, Robert Woodward gave empirical rule by correlating the lambda max values with the molecular structure. These rules were modified by the Lewis-Fisher in 1959. These are the two scientists, Robert Woodward and Lewis-Fisher. These rules were identified by their names. Therefore, they are called as a Woodward-Fisher rules. These rules depends upon the basic skeleton of the organic compound and the substituent present in the organic compound. These rules are used to calculate the lambda max values of the organic compound, and the organic compound may be a conjugated diene, trine, or enone or aromatic compound. The rules for diene and trine, in this case, we have to choose a parent diene. Parent diene, it may be acyclic diene, heteroannular diene, homoannular diene, acyclic trine, and they have a different base value. Acyclic dienes and heteroannular diene have base value 214 nanometer, whereas homoannular diene it is having 253 nanometer base value, trine 245. Then the nature of substituent on the organic compound or present in the organic compound. If alkyl group is present, in case of acyclic diene, then it is having value 5 nanometer. We have to add this 5 nanometer into the base value. These are the increment or addition of the wavelength. In case of cyclic diene, these alkyl groups, they are considered as a ring residues. Then alkoxy group 6 nanometer we have to add. For halogen, that is chlorine bromine, 5 nanometer. For oxygen or acyloxy group, 0 addition is there, and for thioether we have to add 30 nanometer. This is about the nature of substituent present in the organic compound. Now, for the double bond, if the double bond is used or it is present in a conjugation with the parent diene system, then we have to add 30 nanometer. And if the double bond is present in the cyclic diene and it is exocyclic to the one ring, it is having value 5 nanometer, that value we have to add in the base value. This exocyclic means the bond which is present outside the ring but attached to the ring through one carbon. If the double bond is present outside the ring and exocyclic to the two ring, then we have to add 10 nanometer. Now we will see the meaning of acyclic diene, heteroannular diene, homoannular diene, extended conjugation, and exocyclic double bond. Type of diene and nature of double bond. The dienes are classified into three types, that is acyclic diene, semicyclic, and cyclic diene. Acyclic dienes are also called as a linear diene. Here a cyclic ring is may be present or may not be present, but the double bonds which are in a conjugation, they are not present in the cyclic ring. So this type of structure, it is called as acyclic diene, and here double bond and then single bond, then double bond. The double bonds, they are in a conjugation, so it is called as a diene, but it is a conjugated diene. So when this type of structure is also present, it is also called as a acyclic diene, though it is having a cyclic rings. But the conjugated diene, they are not part of this cyclic ring. That's why these are the acyclic diene. Semicyclic diene, it means that the conjugated diene is having one bond in a cyclic ring and one bond outside the cyclic ring. So this type of basic skeleton is present, one bond is present inside the ring and one bond outside the ring. That dienes are called as a semi-cyclic diene. In a cyclic dienes, we have two types of diene, that is homoannular and heteroannular diene. So in case of cyclic diene, there are two cyclic rings or one cyclic ring which are having two double bonds. So let us consider first homoannular diene. Homoannular means two double bonds present in one ring and they are in a conjugation. So let us consider the rings here. So it is the first ring A and it is the B. I will write here A, B, here A, B, then here A and B. In all these A and B rings, double bonds, they are in a conjugation and present in one ring. So it is called as a homoannular diene. Now in this structure, these are the bonds. In this structure, these are the two bonds here, and here also double bonds are present which are conjugated one. Now in a heteroannular diene, it means that hetero means different. Two double bonds, when they are present in a two rings and they are conjugated, then it is called as a heteroannular diene. This is the ring first here, second, then in this A, B and C. Here one double bond is present in a A ring and one double bond is present in a B, but they are in a conjugation. Now here A, B and C, A possesses one double bond whereas B possesses second double bond which are in a conjugation. Now here we will see the nature of double bond. Now I will write here A and B and here A. Now nature of the double bond. In this point we will discuss the endocyclic double bond and exocyclic double bond, because for exocyclic double bond here you can see if one double bond is exocyclic to one ring, there is an addition of 5 nanometers. So let's take the example here. First one, this is the ring and this double bond is just outside the ring, but it is attached to this carbon, which is the carbon of this ring. So this type of bond, it is called as a exocyclic double bond. The bond which is outside the ring but attached to that ring through one carbon. So in this case, here this is the bond which is called as a exocyclic double bond. Now here this bond is also called as a exocyclic double bond. Then in this case the ring B is there, but here it is the exocyclic double bond. Here for B it is the exocyclic double bond. Here it is also exocyclic. I am saying only the exocyclic nature, not the diene system. So now in this case this double bond is attached to two carbons of this B ring. Therefore, it is not the exocyclic double bond. If it is attached to one carbon, then it is the exocyclic. Now, in this case, this is the exocyclic double bond. And in this case, for ring A, this one is exocyclic. For ring B, this double bond is exocyclic. So, to calculate the lambda max values of diene as well as trine, we need to identify the nature of diene, that is acyclic, semicyclic, cyclic, encyclic, homoannular or heteroannular. On that basis, we have to choose the base value. It may be a 214 nanometer or 253 nanometer. And after the identification of the basic skeleton, we have to look upon the exocyclic double bond and conjugation, that is extended conjugation, or the substituent present on that diene system. In the calculation of lambda max for various diene, one thing is clear, that the diene should be a conjugated one. Then and then only we can calculate the lambda max. The conjugated diene means having the structure like this: double bond, single bond, double bond. It means that two double bonds must be separated by one single bond. So for the calculation of lambda max, we have to use this formula, that is lambda max is equal to the base value plus substituent contribution plus other contribution. Substituent means it may be a ring residue in case of cyclic diene. It may be a alkyl in case of linear or acyclic diene, or halogen or thioether group, or acyloxy or alkoxy group. Other contribution, it indicates the presence of double bond, that is extended conjugation or a exocyclic double bond. Now the first example in this calculation is having a acyclic diene system. This is the acyclic diene system. Therefore, the basic value for this compound is a 214 nanometer because it is the acyclic diene. Now there is a absence of extra conjugation. Then here all the alkyl groups are attached here. That's why we have to write alkyl substituent. Just calculate them. This is the first, second, and third. So here we have to write alkyl substituent. Three substituents are present, so 3 into 5 it is equal to 15. And other than this, there is no substituent as well as no exocyclic double bond. So just we have to add this value, and here we get a 229 nanometer. This is the lambda max value for this compound. Then the second compound, first thing is that we have to identify the basic skeleton, that is parent diene. So the parent diene, it is extend from this carbon to this carbon. Now here no extra conjugation on this carbon, no extra conjugation, and this is the acyclic diene, so base value is 2414 nanometer. Then this is the alkyl substituent. This is the second alkyl substituent, so I have to write here alkyl substituent. 2 into 5 it is equal to 10. Then for this group, this is the another substituent than alkyl. This is the OCH3, that is alkoxy group. So I have to write alkoxy substituent. One substituent is there, so 1 into 6, so I have to write here 6. Then just adding this, we get 230 nanometer. This is the lambda max for this compound. For third compound, just we have to identify the parent diene system. This is the parent diene system. It is a cyclic one, therefore lambda max value, that is base value, is 214 nanometer. Then now identify the substituent. This is the first alkyl substituent. It is the second. So I will write here alkyl substituent, that is 2 into 5 it is equal to 10. Then other than this, this is the acyloxy substituent and this is the thioether. So for acyloxy substituent, just we have to add 0, and for thioether, that is S and R. Here S and CH3 is there, therefore we have to add here 30 nanometer. So by combining this, we get here the value is 4, then here 5, and here 2. 254 nanometer is the lambda max value for this compound. Then for the fourth compound, first of all, we have to identify the parent diene system up to this carbon. From this to this, it is the parent diene. So value is 214 nanometer. Now there is a single bond and double bond after this double bond, so this is the extra conjugation. From this it is the extra conjugation, so I have to write here extended conjugation. Extended conjugation. So extended conjugation, we have to add 30. Then afterwards we have to identify the substituent. This is the first alkyl substituent, this is the second, this is third, and this is the fourth. So 4 alkyl substituents are there. So I will write here alkyl substituent. 4 into 5 it is equal to 20. Other than this, no exocyclic double bond, no other substituents. So just add them. Here we get a value 264 nanometer. In this way, we can calculate the lambda max values for diene. Now consider another examples. So in this example, here you can see, in this example there are two rings and the double bond present here. This is not a cyclic diene, it is the acyclic diene, because our parent diene system is present here, which is outside the ring. Now this is the ring, this is the ring, so I will write here A and B. Then the base value for acyclic diene is 214 nanometer. Now we have to identify the substituents. Here it is the substituent, this is the second, this is third, and this is fourth substituent. Now these substituents are the part of a cyclic ring. Therefore, rather than having a alkyl substituent or saying alkyl substituent, we have to set here uh, ring residue. So there are a ring residue and the number are 4. 4 ring residue into 5, it is equal to 20. We have to add 4 ring residue. Then for ring A, this is the exocyclic double bond. For ring B, this is the exocyclic double bond. So exocyclic double bonds are present. Exocyclic, I will write here double bond. Then how many? 2. 2 into 5, it is equal to 10. And then no extra conjugation, so just add them together, and here we get a 4, then here a 4 and 2, 244 nanometer. This is the lambda max value for this compound. Then next compound, this is the ring A. Now it is the semi-cyclic diene system, because one double bond is present inside the ring and one outside the ring. Now for semi-cyclic, again the value is 214 nanometer. Now here it is the one alkyl substituent and these two are ring residue. So I will write here alkyl oblique ring residue. So total 3 are there. So 3 into 5, it is equal to 15. Now no extra conjugation. This double bond is not a exocyclic one. So we have to add just a 229 nanometer. This is the lambda max value for this compound. Then for this compound, in this compound, this is the ring A and this is the ring B. Now in a ring B, one double bond is present and the ring A possesses two double bond which are in a conjugation. Therefore, the cyclic system, it is like this, that is the parent diene system, and here two double bond are present in one ring. That's why it is the homoannular diene. So here I will write homoannular diene, and for homoannular diene the basic value is 253 nanometer. Now beyond this, no conjugation. Here just we have to identify the ring residue, because cyclic system is there. So I will mark ring residue. This is the first, this is second, third and fourth. So ring residue I will write here 4 into 5, it is equal to 20. Then here for B ring, these two double bond, they are exocyclic. For A ring, no exocyclic double bond. So exocyclic double bonds are present here and the exocyclic double bonds are 2. So 2 into 5, it is equal to 10. So total value, it becomes, when we add this, we get here 3, then here 8 and here 2. 283, it is the lambda max value for this compound. It is having homoannular diene system. Now the next examples are, so this is the example where we have a two ring A and B. A possesses one, B possesses another double bond, and these double bonds are in a conjugation. So here a heteroannular diene system is there. So the basic value is 214 nanometer. Now a ring residue we have to identify. This is the first, second and third, sorry, third ring residue is present here. So ring residues are 3. 3 into 5, it is equal to 15. Now other than this, no extra conjugation is there. we have to identify the exocyclic double bond because cyclic system is there. Therefore, for ring A, this double bond, it is the exocyclic because it is just outside and attached to one carbon. So one exocyclic double bond, exocyclic double bond. So here 1 into 5, it is equal to 5. Then we have to add this, and here we get a 234 nanometer is the lambda max for this compound. Then next is the compound having two ring. Here in ring A, there is a two double bond which are in conjugation, and this double bond is in conjugation with this. So up to this carbon, it is the homoannular diene, and from this carbon up to this carbon, it is the heteroannular diene. So there are two choices in front of us, but we have to choose homoannular diene because it is having maximum value. So in such a cases, when we have to choose, we have to choose the homoannular diene. So here I will write homoannular diene 253 nanometer. Now this conjugation, it is considered as an extended conjugation because it is in a conjugation with this diene system. So there is an extended conjugation, and it is having 30 nanometer addition. Now ring residue, this is the first ring residue, this is the second, and this is the third ring residue. So the ring residue, 3 into 5, it is equal to 15. Now next is the exocyclic double bond. For ring B, this bond, it is the exocyclic double bond, and that's why here one exocyclic double bond. So I will write here double bond 1 into 5, it is equal to 5. Just add them together. Here we get I think 303 value. It is the lambda max for this compound. From this example, it is clear that when there is a presence of heteroannular diene and homoannular diene in one example, then we have to choose a homoannular diene as a parent diene. Then the next example, it is having three rings A, B, and C. In this case, this is the diene system. It is the heteroannular, and heteroannular we have to add a base value 214 nanometer. This pi bond, double bond, it is not in conjugation with this systems. Therefore, we neglect this. Now, ring residue, this is the first, this is second, and this is the third. So three ring residues are there. So ring residue 3 into 5, it is equal to 15. Then exocyclic double bond for ring A, this bond, it is the exocyclic double bond. Therefore, exocyclic double bond 1 into 5, it is equal to 5. Now no another substituent, so that's why here we have to add this, and it becomes 234 nanometer value. Now in the last example, there are three rings A, B, and C. Now there is a presence of two diene system, that is from this carbon up to this carbon, it is the heteroannular diene. From this carbon up to this carbon in the ring B, it is the presence of homoannular diene. So in front of us, there are two choices, and we are going to select this homoannular diene as a parent diene. So the value is 253 nanometer. So I will write here homoannular diene as a parent diene. Then ring residue, this is the first ring residue, this is the second, this is the third, and this is the fourth ring residue. So the ring residue, that is 4 into 5, it is equal to 20. Now consider the extended conjugation. So this is the diene system, and beyond which there is a single bond and double bond. So this is the extra conjugation. So just we have to write here extended conjugation, extended conjugation. And how many conjugations? One. So we have to add 30 nanometer. Now here, as there is a presence of ring, we have to consider exocyclic double bond. Now in this system, for ring C, this bond, it is the exocyclic double bond, and for ring A, this bond, it is the exocyclic double bond. So exocyclic double bonds are 2 exocyclic double bond, that is 2 into 5, it is equal to 10. Now adding this, we get here a 313 nanometer. It is the value of lambda max for this compound. In this way, we can calculate the lambda max values for various diene. It may be a acyclic one or a cyclic one. It may be a homoannular one or a heteroannular one by using Woodward-Fieser rule. In the next video, we will see the calculation of lambda max values for enone system.